And so today he's going to give a talk on this CMB as a backlight. And please,
okay, great. Thanks so much, Tim. Thank you so much for the invitation. It's so nice to be here. This is
your microphone on?
I turned it on green.
Okay,
Can people hear me okay?
Yeah, it will be fine.
Okay,
It's mostly for the online people.
Okay, so I don't need to yell. I can just talk about this one.
you already got the thumbs up there.
Okay, perfect. Yeah, so like I was saying, thank you so much for the invitation. It's great to see all of you. And I'm sure everyone's happy to have Colloquia back in person, just like I am. This is the first time I've spoken in front of people in about 3 years. So if I'm a little rusty, please forgive that. But I'll do what I can. So let's get on to the science. So it's called the CMB as a backlight. So I'm going to talk about what I mean by that. And then I'll talk about some of the general research programs that we're doing in the CMB community to use the CMB as a backlight. And I'm just going to focus on some particular research projects that I've been doing within this broader scheme of research. Okay, so let's get started. Here is the cosmologist view of the universe. We are at the center. As we look far away, the farther and farther away we look, we're looking back in time, simply because it takes finite time for light to travel to us. So as we look back in time, we're looking back in the past, and we can do that for some amount of time. We see galaxies in their formation and evolution. There's various changes in the universe, but we can keep seeing until some point we can't see anymore. Because beyond this point, the universe is opaque to photons. Now, this is the cosmic microwave background. This is the light that's left over from the Big Bang, from the early universe. And the general research program that I hope to convince you is interesting that I'm working on is this idea of using the CMB as a backlight. We have these photons coming to us from this very far away surface, and they're traveling through the whole universe. And when we see them, they have all these imprints of all the structures along the line of sight. So we can learn things about not just the CMB surface itself, but all the way through cosmic history. Okay, so that's the general takeaway point that I hope everyone remembers about this talk, details aside. Okay, so let's zoom in a little bit about what the history, what these epochs in cosmic history actually are. So I'm going to take a slice now through the universe, looking out in distance or equivalently looking back in time. So let's look at that. Okay, so here's that vertical kind of slice that I showed before, but now in a little more detail. So on the left-hand side, you see years since the Big Bang. So counting from the Big Bang forward, 0.3 million years is where the cosmic microwave background is released. And then today, the universe is 13.5 billion years since that time. Okay, but when we look out, we're looking back in time. So we can look at all the different epochs that we've been through, the formation of the solar system, the evolution of galaxies, which is one of the things that we work on in my group. Completion of the reionization. So what's happening around this time is when the universe went from neutral to ionized. When the first stars turned on, they caused the intergalactic medium to become ionized. The first astronomical objects, so the first stars, are getting formed about 0.5 billion years after the Big Bang. And then as we go past, like I said, the CMB is this opaque screen that we can't see past. Okay, so let's talk about the CMB a little bit. So there's these relatively well-known experiments that have been funded by NASA and the European Space Agency. We've been really lucky in this field to have roughly every 10 years, so every decade, we had another CMB experiment in space that was really pushing the boundaries of what we knew about the microwave background and what we learned about the universe from the microwave background. So first there was COBE, which won the Nobel Prize for first detecting the fluctuations in the microwave background, as well as measuring its thermal spectrum, establishing that the universe was once hot. Right around the time I started graduate school was the era of WMAP, which had finer angular resolution than COBE. And then about 10 years after that was Planck, which had yet higher angular resolution and also more electromagnetic frequencies. If you look at the zoom in here, you'll see that the Planck versus WMAP increase in angular resolution and how much more information that we get. Now, if we take this Planck image, this red stripe that's going through the middle here, this is the Milky Way galaxy. So if we subtract that away, we're left with this. So you may have seen this picture before. This is from the Planck experiment. And this is our best picture of what the universe was like very shortly after the Big Bang. So this is the universe's baby picture. These hot and cold spots are representing gravitational potentials that we believe will evolve and turn into the large-scale structure that we have all around in the universe today. So this is giving us a great picture of what the universe was like at early times. And I have a slide here telling us the statistics of that previous image. And the main thing to learn from this image, to me, is let's look at this plot here. So this is the so-called power spectrum that's breaking down these fluctuations as a function of angular scale. So if you take that CMB map and you ask, how bright are the fluctuations on a given angular scale? That gives you a plot on the right. And there's three things about this plot on the right that are interesting to me. The first thing is that we have this solid theoretical prediction in blue. And then the second thing is just how good those data points are in red. Those error bars are absolutely tiny. And then the third thing is that the data and the theory agree with each other perfectly. So we understand this early time in the universe, I would say perfectly, so far as we can observe it. To get this theory curve, it's relatively simple. It's using physics that we understand by treating these various interactions between these fundamental particles that existed at that time. We're able to produce that spectrum. So we have a pretty good picture of what was going on right after the Big Bang. In particular, that model, you need to have certain components in that model. So you need to know the densities of various things that are in the universe. You need to know something about the amplitude and shape of the fluctuations as a function of angular scale. And these are some great things that we can extract. We haven't really seen any compelling evidence for any physics beyond this, although there are some tensions, okay, which I'm not going to talk about. So maybe we're done with the CMB, right? So one question you might have is, why are we still talking about the CMB in 2022? And the answer, of course, is the title of my talk. The CMB is a backlight. So we have much more to measure, and to me, that's from the perspective of using these photons, not to study them, to learn about the early universe, but to really trace all of cosmic history between the time of the release of the CMB and today. Okay. Stop here if there's any questions on the broad picture here. Okay, I'd like to move on to the CMB as a backlight. So here's a really nice image that collects all of the effects that I was referring to of things that happen to the CMB photons as they go through the universe, and they can undergo various different types of scatterings or interactions with the objects in the universe. So we can go through these from left to right. I really like this figure because I don't know of any figure that better encapsulates just about everything I've ever worked on in one figure. Okay, so one thing that might happen is a CMB photon can come in and it can hit a hot electron in the deep gravitational potential well of a galaxy cluster. And if it does that, it can undergo content scattering and change its angle and change its energy. And then we can actually see this galaxy cluster in our maps of the microwave background. So that's called the Sunyaev-Zel'dovich effect, SZ effect. There's the integrated Sachs-Wolf effect, which happens because dark energy becomes important at relatively recent times, and this has a characteristic impact on those CMB photons. These next two, Doppler and Vishniac, are different flavors of what I'm going to talk a bit about later, the kinetic Sunyaev-Zel'dovich effect, which happens when electrons are not hot, but they're moving. So there's arrows, these green arrows here represent the fact that the electrons are moving. The other thing that I'll be talking about today is this gravitational lensing. So if you look closely at this blue line here, there's a bend to it. Can you see the bend? This bend is happening because the path of the photon is being disturbed, perturbed, if you will, by the large scale structure between us and the CMB. So that's the other thing that I've spent a lot of my time thinking about. Patchy reionization is something I'm also going to touch on briefly. That's a similar idea. You have an electron moving along the line of sight, and it gives you a scattering, and it gives us a signal in the microwave background. And I'm going to show images of that effect a bit later on. Okay. Okay, so here's the outline of my talk, a bit more about this idea of using the CMB as a backlight and the overview of the experiments that are going on right now to measure this. And then the rest of the talk is going to be broken down into two themes, baryons and dark matter. And I'll give some examples of things I've worked on related to both of those things. Okay, so we have active surveys right now, just to get a sense of the experimental landscape. So in my PhD, as Tim said, at McGill, I was working on the South Pole Telescope. This is the big 10-meter dish down at the South Pole Station, right at the bottom of the Earth. And then for my postdoc and now faculty, I'm working on the Atacama Cosmology Telescope, which is in Chile. It's a smaller dish, but it's going after most of the same science goals. So I'll lay out in a second. ACT is being succeeded by this new project called the Simons Observatory, which is going to be built next door. So here's a computer sketch of what that looks like. So we've got the ACT telescope up there. And then the Simons Observatory is a similar size dish together with some smaller ones. And then for anyone keeping score of all the different CMB experiments, I've got this handy slide to let you know which groups come from which. So ACT and Polar Bear, which are both at the Atacama, are coming together and currently building the Simons Observatory. So right now we're analyzing ACT data, we're building the Simons Observatory, and we're planning for CMB-S4, which will also be together with these other two experiments that are at the South Pole. And we are very happy that the CMB-S4 was quite highly ranked in the recent Astro 2020 decadal, so it looks like that will go forward, hopefully. So these are from the ground. And then from space, it looks like a new satellite. So we missed one in the 2010s, but in the 2020s, we'll have one called Lightbird. And then we have a proposal that I've been involved with for a US-led mission called PICO. Okay, let me pause this for a second. Okay, why do we want to do something past Planck, or why is it that from the ground we can in principle do better than this amazing Planck data? And it's really a combination of angular scales, so you can get a bigger telescope. You can't launch a 6 or 10 meter dish into space. So we have better angular resolution from the ground than we have from space. And if we integrate long enough, we can also have better depth or better sensitivity in our data. And so these two things come together in a nice image like this. What we're going to see now, this is a map of the cosmic microwave background. There's all these background hot and cold spots. These are the temperature fluctuations left by the Big Bang. And then we have these bright spots, which are galaxies that are emitting in these frequencies. These galaxies are more nearby than the microwave background. Some of them are radio sources. Some of them are dusty star-forming galaxies. What's going to happen is we're going to kind of pan across a piece of the CMB sky, and we'll pan across it, and we'll see the same piece of CMB sky in both ACT and Planck. And as the features move from right to left, the thing to notice is the fact that the noise is much reduced, and also the point sources become smaller because the angular resolution is better. So there you go. So the upshot here is that from the ground at the ACT telescope, we can just see a lot more detail, and therefore, quantitatively extract a lot more science than we can from the Planck maps of the given same angular size. Okay. Here's a view of the CMB experiments, the way that we like to kind of, the two yardsticks by which they can be measured. One is the depth down to which they measure. So this is kind of the noise level. It is the RMS noise in the pixels in the image on the y-axis. And then the number of modes here, which is a combination of how big is my survey. So the satellite images you saw were full sky. The ones from the ground are not full sky. So you have the angular size of your survey, and then the resolution. The more modes you can measure, basically the more science you can get for pretty much everything that we would want to measure. And you see that if you look at the years of these experiments, they're pushing down and to the right. in many ways, that some of the ACT data that we have in hand, some of the results I'll show you is from results that are quite a bit beyond, down and to the right of where Planck is. And then with Simon's Observatory, that pushes things even further down and to the right. These two halves of this graph are split up into two halves. The science you can do with large scales, and then the science you can do with small scales. I'm only going to talk about the small scales. Okay. Everything on this list is something that falls under the CMB as a backlight theme. Okay. CMB science. So what can we learn? So this is the image from the front cover of the proposal for a probe class NASA mission that I was involved with. And I really like this image. It's prepared for us by JPL artist. But it really kind of encapsulates everything that one could still hope to do with the microwave background. And what you see is that these different arrows are pointing to different times in cosmic history. So there are some, my mouse work? No. There are some that are pointing to the CMB surface, and there are still some things we want to get from the CMB surface. Things like how many relativistic species are there? Did inflation happen? And we are pursuing those things, but the CMB as a backlight theme refers to everything that has the arrow that is ending somewhere in between here. Okay, so in particular, I'm going to talk about dark matter and then cluster evolution. Okay, so let's talk about cluster evolution first. So this is baryons around halos. So I'm going to start with one example of the CMB as a backlight. Okay, coming back to my favorite picture, that's these guys. So there's the Sunyaev-Zel'dovich effect, the thermal Sunyaev-Zel'dovich effect from these hot electrons. And then there's when these electrons are moving along the line of sight, that's the kinetic Sunyaev-Zel'dovich effect. Here's another cartoon of what's going on with these effects. Again, the thermal effect is when a CMB photon comes in, it Compton scatters off an electron in this hot plasma, and it comes into our line of sight. It's been Comptonized, and its energy has changed. It's on average being given higher energy than it had before. Since it's got higher energy, it means that the spectrum is expected to peak at a higher frequency than it would have if there was no cluster there. And so we see that in our maps as dark spots, actually. This thing is proportional to the pressure. So the number density of these electrons times their temperature. Okay, the kinetic effect is a bit different. That's not coming from the internal energy of the electrons, but rather that you have this collection of electrons in a galaxy cluster, and it's got some bulk motion. It's moving with some speed. When that happens, you get a similar type of scattering effect, but this one is proportional not to the electron temperature, but to the line of sight velocity divided by c. So these are two different effects that we now become very good at measuring in our CMB maps, as I'll show you in a moment. Okay, so why do we want to measure this? So ionized gas is a crucial part of galaxy and cluster evolution. We'd really like to know where are the baryons, where are these ionized electrons. And this nice figure shows you that the thermal and kinematic SE or kinetic SE is a unique way to get this over a wide range of masses of the objects you're looking at. So the y-axis is how massive are the objects, and then the x-axis here is redshift. So in comparison with some other methods, so X-ray is maybe the most established method, but is limited to the most massive objects and the most nearby ones. With the SE effect, you can push this to more far away objects and also to lower mass objects. There's another method of absorption lines, which at ASU, Sanj Borthaker is an expert on. And then fast radio bursts, which are a brand new, exciting new field that's kind of exploded in the last years. Okay. So the thermal and kinetic SE effects are these unique probes of the gas properties. So some science questions that we could ask are, it seems like gas is being ejected from halos. And this seems to be due to feedback from active galactic nuclei, and to some extent supernovae as well. And these are processes that we would like to better understand. And we can do this with our CMB data. Okay, so here's a couple of images of what the thermal and kinetic Sunyaev-Zel'dovich effects look like. So for a chunk of our sky, I think this is a few degrees by a few degrees. Here's a simulation from a group that I was part of. This is the web sky simulations, for those who might be familiar with that. These sims were led by University of Toronto while I was a postdoc there. Here's an image of all these objects in the universe, clusters, and also lower mass halos. And what we're seeing is the integrated pressure of the electrons through these objects on the left. And this is always positive or non-negative. On the right, the kinetic SE is, like I said, it's proportional to the line of sight velocity. Now, a given object may be moving away from us or it may be moving towards us. So if the object is moving towards us, we see a blue shift, and if it's moving away from us, we see a red shift. So a given object might appear red or blue in this image, depending on what its line of sight velocity is. And of course, the most likely velocity is 0, so you wouldn't see that one at all in this map. You do see that some of the objects are in common between the two. So if an object both has a high electron temperature and a high line of sight velocity, it'll appear. Okay, so just to show you some of the database results that we've been getting from these. Here's the thermal SE. So I kept a little sliver of the thermal SE map on my slide just to remind you what this is. So here's a stack of the ACT data on a sample of galaxies that's publicly available that's been very well characterized. The BOSS galaxies from the Long Visible Sky Survey. Here's a stack. So what you do here is you take the ACT temperature data and you look for the thermal Sunyaev-Zel'dovich effect by taking everywhere that you know there's a galaxy. You just average, you take a little stamp, a little cutout, and then you average those together. Okay, and then this gives you this image with a dark spot in the middle. So this is the characteristic of the thermal SE effect. If you plot this as a function of radius, you get the right-hand panel. Is there a question?
No, online participants, please mute.
Okay. And so this is being plotted, and interestingly, there's some difference from this radial profile of these objects compared to some recent simulations. It's illustrious. Okay, so this is an ACT result that we had in the last couple of years. Coming back to the kinetic SE, here's a similar idea. You average your CMB temperature everywhere that you know that there's a galaxy. But for the kinetic SE, like I said, sometimes it's positive if it's coming towards you and it's negative if it's moving away. So on average, you're going to get 0. So instead, you have to do this velocity weighted stack. So for each galaxy, you need an estimate of what is its line of sight velocity. And then if it's moving away from you, you add it in with the plus sign. If it's moving towards you, you add it with the minus sign. So a velocity weighted stack. And the reason that this isn't just a technicality, this is a requirement. And for that, we need to know the redshifts of these objects very well, which is why we do this on spectroscopic samples. But similarly, we've got this radial profile where this is the electron gas now being built up as a function of radius. You can see in arc minutes at the bottom, or for the theorists in the crowd, the megaparsecs up above. And the really glaring thing about this is the fact that this is very different from the NFW profile. So the NFW, the dark matter distribution, is totally different from what the electron gas is doing. So you see just from this plot evidence of feedback or something pushing out the ionized gas compared to what the dark matter is doing from gravity alone. Okay. Pushing these measurements forward in the coming years is something that's going to be, in my view, extremely exciting. The two stacks that I showed you just now are kind of the first proof of principles for these types of measurements. But the CMB data is going to get better with CMB-S4, and then the spectroscopic samples are also going to get better with the DESI experiment that we were just talking about at lunch is ramping up very fast. Now, if a forecast for what this type of stack would do, the thermal SE on the left and the kinetic on the right, shows you how tight these error bars are going to be as a function of radius. or Engelen in arc minutes. And these black error bars are really, really small compared to the dispersion among these different hydrodynamic simulations. So every one of these colored curves is a different procedure for well, a whole host of different effects, but most importantly, feedback, pushing out gas. But each of these sims is relatively recent and is more or less up to date with observational constraints, and yet they predict wildly different predictions for both the thermal and kinetic SE. So I hope this convinces you that we're going to be able to kind of nail down what's going on with these galaxies from this perspective. Okay. Good. I'd like to talk. So this thermal and kinetic SE stacking is going to do even better in the future. I'd like to show you a couple of innovative new ideas that I've been pursuing with some colleagues over the last year or two, based around this idea of looking for the distribution of ionized gas around halos. The first one is called oriented thermal SE stacking. So let's talk about that. Oriented stacking. So this is a project led by Martine, who's a Ph.D. student at University of Toronto. If we just look at the picture, the normal type of stacking that one does is you take your, as I said, you take your temperature map, and everywhere that you know there's a galaxy, you just average together the temperature map at every location of the galaxy. And then at the end, you get this average distribution like I showed. That's unoriented stacking. Oriented stacking is almost the same thing, but you first rotate. So you're looking at the nearby large-scale structure. The nearby realization of large-scale structures might have an impact on the distribution of the gas. So what Martine does is she goes in and finds the nearby axis of the large-scale structure, and before doing the stack, she rotates them all to be collinear. And then she does the averaging or the stacking. And then the question is, when she's finished, is she going to find anything that's aligned with this direction? And if so, that's a way to try to probe how the gas may be interacting with the nearby large-scale structure. And it's a way to look at the distribution of the gas well outside the center of this object that you're stacking on. Okay. Okay, so like I said, this is a unique way to measure gas that's not in the halo necessarily, but outside the halo, potentially along a filament aligned with the halo. So what did we do? So in a bit of detail, I know there's some experts in the audience here. So we took our ACT thermal SE map. We took the DES year 3 clusters, optically selected clusters, and we stacked the thermal SE, or I should say Martine stacked the thermal SE. But she did this by orienting with a large-scale structure that came from the galaxies that were also from the DES survey. So we're using 2 different data products from the DES survey. One to stack on and one to orient with. And then we're stacking the thermal SZ map on this. And this is all thanks to a memorandum of understanding that we have between the ACT and DES teams. Okay. So here's an image that shows you the result of this procedure. So I'm going to talk you through. Let's start, I think, with the bottom, which is the simulation. So this is what we expect from simulation. So here the white circles are a circle around every object in every galaxy cluster. The nearby large-scale structure direction is determined by, I won't get into how she does it, but we find the direction of the arrows as telling you the nearby orientation of the large-scale structure. So what's the elongation direction of the large-scale structure? This is done basically by taking the second derivative, the curvature matrix around each point, and looking at what direction is it curved, and then drawing the vector through the direction, the long direction for the nearby density field. And then if you turn and rotate, you find not only that there's a bright cluster gas in the center of this object, but there's this bow tie shape. So the gas from nearby, from all the halos nearby that central object, are showing up in a way that's oriented. Okay. This is something that I don't think had been quite characterized in this way before. So we kind of identified this as something to try to measure in the data, and then we went and looked in the data. So in the real data is above. So the real data is just like the lower data, but it's much noisier. So the thermal SZ has got a whole bunch of extra noise on it that's not present down here. But nevertheless, we do the same procedure. We take our CMB data, rotate it with the nearby galaxies, and then do this oriented stack. And then you can ask yourself, is there a horizontal bow tie shape in that top panel, as there is down here, putting aside all the noise that you see? Okay, the way to answer that is to do this multipole decomposition. So what we do is we decompose the result into multipoles. So taking that sim result, that buzzard stack, if you break it down into m equals 0, 2, and 4, the m equals 2 and 4 are telling you some sense about the level of anisotropy. The result is that we get something very similar between the observations and the simulations. So the simulations, these are these buzzard simulations that the DES team and their colleagues put together, give you this band in blue, and then the data themselves give you these blue data points. So it's just a few sigma detection right now, but it is a detection of gas that's oriented with the nearby large scale structure. That's for m equals 2. M equals 4, we don't quite have a detection of it. We do see this blue band giving us the prediction. Okay. I'll just take a pause here. Okay. The second new idea. So in addition to the thermal SZ and the kinetic SZ, is some work done on trying to think about yet another way to measure this ionized gas, as if those two ways weren't enough. So the idea here is you're looking through this hot plasma, through this galaxy cluster, at this CMB last scattering surface that's farther away from you. And there's some optical depth here. There's some chance that the electrons are going to be scattered out of your line of sight. And if that happens, that those CMB fluctuations behind it are going to look washed out. Just in equations, the temperature that you see is the actual temperature on the last scattering surface times this optical depth factor. And the optical depth is directly proportional to the electrons along the line of sight. Like this plasma here. Okay. Now this is an effect that's never been measured. But nevertheless, so we thought about whether this could be measured with a future CMB dataset like CMBS4. So here's a map of this optical depth. So every cluster on here is a blob, and this has nothing to do with the thermal motions of the cluster of the electrons in here. This is just a projection of the electron density. So the nice thing about this is it doesn't depend at all on the thermodynamic state of these electrons. And the idea to measure this is you just look, if you look at your CMB, you're looking through this optical depth. So if your CMB map is a bit washed out in some location, that's an indication that there's extra electrons there. So a quadratic estimator where you look for the variance, you look for a local reduction in the CMB variance, and you tag that as a place where there's extra electrons. Because the CMB, the background CMB behind these objects is going to look washed out compared to where there's some spot where there's no object. Okay. This quadratic estimator for this was developed a long time ago, but for looking at a different effect, reionization at redshift 10. We're looking at this at lower redshift halos, redshift less than 3. It's never been observed. Okay, but we had a theory forecasting paper led by Anirban, who's a postdoc at Cornell, showing that this will be observed with LSST together with CMBS4. So the idea would be to make an image of those electrons and then correlate those with the locations of galaxies from the LSST survey. And we will measure that according to our paper. So signal to noise of about 13. So that's nice because you're measuring something similar to the kinetic SZ, but you don't need those redshifts. So like I said, we needed spectroscopic redshifts for the kinetic SZ, but not here. Also, you could argue that this is a cleaner measurement because there's less complications in the measurement than there is for the kinetic SZ. Okay, so this is a paper that I wanted to just share that we just put out a few weeks ago. Okay. Any questions on the baryon part of this talk? Okay. So the next 15 minutes or so, I'd like to finish on CMB lensing. So we were talking about baryons for the last 30 minutes or so. Let's talk about dark matter. Okay, so we talked about the SZ effect and the kinetic SZ effect. Let's talk about lensing, which is the fact that the paths of photons are slightly bent by the large scale structure from the CMB to us. Okay. Here's a cartoon of this. So you've got your CMB last scattering surface. You've got us, the observers, down here. And then as these photons come through the universe, their paths are going to be bent by the large scale structure. So this is a movie. Okay. So when we look out at the CMB last scattering surface, the image that we have is slightly distorted. And we can use this fact to measure the dark matter between us and the CMB. And this is what I did my PhD on, and I continue to work on that. Okay. How do we measure this? So the top picture is something that we have a lot of expertise here at University of Arizona, is how to measure lensing from galaxies. The way that that's done is if you have some set of objects that have some natural shapes, if you put a blob of matter in front, it's going to change the shapes of those background objects in the way that you see in the top two figures. With the cosmic microwave background, it's exactly the same thing. The difference is the objects that we have, whose shapes that we know, are these hot and cold spots on the last scattering surface. And right at the beginning of the talk, I said that we understand everything about these hot and cold spots because that theory curve for that power spectrum went right through those data points. So we have something whose properties we know perfectly, which means the distortions that lensing induces can be identified because it changes the shapes of these hot and cold spots. So I'm not going to get into the machinery of how we make these CMB lensing maps, but physically that's what's going on. We're looking for the changes in the shapes of these background CMB hot and cold spots. So in this example, we would infer that there's a positive mass object in the center. Okay. There's some advantages to the cosmic microwave background compared to optical galaxies. We know it's redshift, so unlike with optical galaxies, where experts who work on that have to worry about the distribution of where those galaxies are, we know exactly the redshift of the CMB, where it's coming from. It's at a single redshift, and it's behind everything. So, like I said, it's the farthest that we'll ever be able to see in the universe. And so every piece of mass in the universe is in principle lensing the cosmic microwave background, no matter where it is. And then, like I said, the statistical properties of these hot and cold spots are completely understood. Just to give you a sense, I've been showing this figure for many years, but this is just to give you a sense of the size of the effect. So here's a 10 by 10 degree chunk of the cosmic microwave background temperature. There's no clusters, no thermal SZ, nothing in here, just those hot and cold spots left over from the Big Bang. This is the unlensed one. Now what's going to happen when we do lensing is these hot and cold spots are going to shift around a little bit. They're going to shift by a relatively small amount, a couple of arc minutes on this 10-degree scale. But the shifts are going to be coherent over big chunks of it. So you're going to see big chunks of it move, but then they're not going to move very much. So like this. Okay, so I like to blink between these and ask, can you measure that this one is different from this one? And that's the kind of the game of high precision measurements of CMB lensing, is really distinguishing in detail this image from this one. Okay. If we do, here's the lensing field on the left that was causing the CMB hot and cold spots to move around and change their shape. And then on the right is our reconstruction. And this is actually this figure is actually quite out of date now, and even at the high noise level that we had when I made this figure, we're still able to see that there's a lot of structures in common between the reconstruction and what went into it. And one technical point I want to note too is that unlike in cosmic shear optical lensing, our reconstruction comes both from the change of shape of the hot and cold spots and also the change in size, so the magnification factor. Both of these effects are included when we do our reconstruction, with about the same weight or on the same order. Okay. So just an overview of the state of the art of measurements of CMB lensing and what cosmology we can get from it, going from our current survey ACT, Simon's Observatory, and then CMBS4. Okay. So here's another picture of the Atacama Cosmology Telescope. Like I said, this is a 6-meter dish in the Chilean Atacama Plateau. It's there because it's a very dry location. So water vapor is your enemy when you're measuring the cosmic microwave background. So they're really the only two sites that anyone uses nowadays are the South Pole and the Atacama Plateau. Often photos of the ACT telescope are taken from the ground, and they show you this thing around the telescope. This is just the ground shield that's there to block thermal pickup, including from those mountains in the background. The telescope itself is right. And in this team, going back to 2007, we've been just scanning the sky every single night. And we've been upgrading the receiver. We've been putting in more sensitive detectors. We've been scanning at more frequencies, electromagnetic frequencies, through all these various upgrades whose names are written here. But this telescope is taking data every night, and it also takes data during the day. We've never used the data from the day, but we have it all sitting like this. Okay. Here's just a photo of the team. This photo is, I think, from one of the last collaboration meetings we had before the pandemic. So it's a few years ago. Okay, just to show you the increase in size and sky coverage of our data, I'd like to just show you some of the coverage maps. Okay, so this is a full sky image of the Milky Way galaxy, seen from the ground. So our first season of the polarization sensitive detector, which is around the time that I joined the team, 2013, we scan these relatively small patches around the equator of the sky. The reason to do the equator is just that there's a whole lot of other data at other wavelengths there. Okay, the next year, 2014, we had larger patches, and also the receivers were upgraded to more sensitive detectors, so that was a big step forward. 2015 was quite similar, but then in 2016 and later, we've been doing these huge swaths of sky, or we're essentially mapping out the whole sky that we're able to see from the latitude of Chile. And what this means is we're able to, like I said, what you want is a large sky fraction divided by angular resolution squared in terms of number of modes. So we're really going after that large sky fraction here. So this is 28% of the sky, which is getting to the order of what the satellites have been able to achieve. And this is a map of the 2016 coverage. The few seasons after that have been upgraded, but with a similar strategy. Okay. Now let's just show you some of the data. So here's some of the CMB maps with the hot and cold spots. Now, in the context of CMB lensing, we run our lensing estimators, which, like I said, look for the changes in the shapes of these hot and cold spots and try to infer where the dark matter is. Here's what that looks like. So if we run our lensing estimator on this, which I could give a whole talk about how it works, but instead I'll just show you the result. Here's a map of dark matter. So this is a map of only dark matter. We filtered out the noise-dominated scales. So what you're seeing here is actual overdensities and underdensities of the dark matter in the universe. This is from that 2014 data. Up here is one of those smaller patches from 2013. So all matter in the universe, including dark matter, in projection. So one thing you don't get to do with CMB lensing that you can do with optical lensing is slice it up in redshift shells. We just have one redshift shell because we only have one source redshift. Okay. Now I just want to show how much this field has jumped forward. So around the time of my PhD, this is what things look like. So this is the variance in that map as a function of the inverse of the angular scale. And at the time, the ACT and SPT teams had each measured this at a few sigma. Now, fast forward 20 years or so, we've got a whole lot of measurements here. Most of all Planck. So Planck has measured this thing at 40 sigma precision, so to a couple percent. Just about every CMB survey has measured this too to varying degrees of precision, but they all generally agree on this prediction. The black curve is a prediction from the lambda CDM model. And it obviously goes right through these points. So this is one of the big legacies of the Planck survey. Okay, why do we want to measure this? So one reason to do this is neutrino mass. So here's a kind of cartoon, highly exaggerated, excuse me, showing you what the effect of neutrino mass is. So if you have massive neutrinos, you have some component of the matter budget that doesn't really cluster because neutrinos have a high free streaming velocity. So as you turn up the neutrino mass, you see there's less time for structure to grow appreciably than a model with small neutrino masses. And we know that neutrinos have mass because of oscillation data, ground-based data. And so one of our main goals in cosmology is to measure the masses of neutrinos using cosmological data. And CMB lensing is one of the best ways to potentially do that. So that's where we're going. Here's a forecast. So I showed you that 40-ish sigma data set from Planck. CMB-S4, what we're hoping to build soon, we'll measure this to 500 sigma, or in other words, 0.2% precision. So that's an order of magnitude better than what we have with Planck. This is a figure that was made for the CMB-S4 science book. And those error bars are so small, I don't know if you can see them. These gray error bars are so tiny that you can't really see them. So instead, we have a zoom in on the bottom panel showing you the error bars in gray, the precision with which this power spectrum will get measured, against different predictions for the neutrino mass. And these error bars can clearly distinguish between these different predictions for the neutrino mass. So our goal for the next 5 to 10 years is to do this measurement. Okay. This is going to be really hard. So I want to just sketch out some of the things that we're going to have to deal with without saying much about them. So one thing is that our lensing estimators that we used to go from the CMB temperature map to the lensing map to the lensing power spectrum, which is where we ultimately compare data with predictions. They're not good enough. So our theoretical tools need to be better. So I'm working in that area a little bit. Also foregrounds. So those thermal SZ and kinetic SZ objects that I was telling you are really great to learn about baryons with. They're a major headache for CMB lensing. They just come in as these big bright objects that you can try to clean them out as best as you can, but we haven't totally solved the problem of getting rid of this foreground effect. So that's been studied a fair bit in the literature. And finally, what I'd like to focus on in the remaining, I'll just spend a few minutes on this, is the baryonic effects. So these are uncertain, just as with cosmic shear lensing. Baryonic effects are uncertain and are going to be important for this measurement. So let me just talk about that. So the baryonic effects and mitigation. Okay, so baryons and CMB lensing. I was telling you that it's going to be great to measure these baryonic distributions to learn about galaxy evolution, and that's true. But the flip side of it is that baryons are a piece of the theory puzzle that we haven't quite nailed down. So if our goal is to measure something fundamental in physics like neutrino mass, uncertain baryonic physics, or in other words, AGN or supernova feedback, is going to present a challenge. Okay, so this top panel is showing you different predictions for the matter power spectrum, which is really what the CMB lensing is measuring. And what you see is that, so I told you that neutrino masses suppress this power spectrum. Baryons also suppress this power spectrum on the scales that we will measure before they start shooting up again. So what's shown here is the ratio of the matter power spectrum with baryons to without any. And all that's happening here is if you have the gas being pushed out of those halos, like I was talking about, the halos are less centrally distributed than they were before. And so you get a reduction in the power spectrum of the statistics. Okay. This is well known to be an issue for measuring cosmic shear. And then you can ask the question, does this have an impact on CMB lensing? So that's what we've been investigating. The answer is yes. So this is a concern for CMB lensing, just like it is for cosmic shear. So it's a bit less of a concern because the CMB, like I said, is farther away. And it's looking at redshifts where baryons should be less important. But it's going to be a concern. So that's what we're showing here. This is a project led by, at the time, an undergrad student who's now a Ph.D., together with Simon Foreman, who's a postdoc currently at Perimeter Institute. And what you see is that each of these different theory predictions, our hydrodynamic sim predictions, gives you a different colored curve here. And they're all dipping below, many of them are dipping significantly below the statistical error bars for these measurements. And the problem is we don't know which of these colored curves is the correct one, if any. So that's an issue. Here's another way of looking at the same thing. The suppressed lensing signal from neutrino mass coming from the slower growth of gravitational potentials in the case of a high neutrino mass. It gives you this suppression shown as the black curve, but then these baryons also give you a suppression. So how do you, if you see a suppression in your measurement, how do you tell which one is right? Whoops. So here's a plot of how much this is going to be in effect for neutrino mass measurements. So what's shown here is if you just focus on the blue points, the statistical error bar is shown in blue. And then the amount of bias, if you ignore the fact that baryons are there, you're going to find that you have a higher neutrino mass than what you actually have. So that's a concern. And also the amount of this bias varies significantly depending on which of these hydrodynamic sims you trust. Okay, they can be biased high by a couple sigma. Okay. So we looked at a few different mitigation strategies with this PhD student who's now moved on to a postdoc position, Fiona McCarthy. 3 different mitigation methods. I'll just say these very quickly. The first one is just to reduce L max. So this, you notice that as a function of L, function of scale, the 2 dependencies were quite different. So why not just throw away the high L modes? This is probably the most tried and true method of dealing with baryons in cosmic shear. You throw away some of your data because you don't trust it as much. The second one is to use a low redshift lensing survey like LSST as a baryon proxy. So since the baryons are affecting low redshift, let's use LSST, not because we want to learn about cosmology from LSST, but because it's doing a really good job of measuring the baryons in the lensing. That was our second method. The third one was to try marginalizing using an analytic prescription for what the baryons are doing, using in this case a particular model, need it all. And the answer is that this works pretty well. You need to use method 1 and 2 together, or method 3. Method 1 and 2 doesn't quite get you there, either one on its own. But you can either cut L max and do this low redshift LSST subtraction, or you can marginalize over this analytic model. Okay, so I think that's where I'd like to stop. Okay, my takeaway message that I hope everyone remembers is the CMB as a backlight. There's lots to be discovered using the CMB, not to measure that primary CMB surface, which again, we basically know everything about, but rather everything between us and the CMB. Of course, there's a big asterisk there, but let's just focus on the theme here, the CMB as a backlight. Okay, I talked about baryons around halos, thermal SE and KSE stacking. I talked about that oriented TSE stacking where we got that bow tie shape, and we found that in the data as well in the simulation. So this is kind of a new way of looking at the SE effect. I talked about this new way of measuring the screening of the background CMB fluctuations, which is different from KSE. Then I talked about CMB lensing and showed how these measurements are on an upward trajectory towards hopefully measuring the neutrino mass. And then finally coming back to these baryonic effects, not as a signal of interest, but rather as a pernicious source of bias, and showed that it's important that we can mitigate it. Okay, so I'd like to stop there and thank you very much. And I'll take any questions.
So you had a plot for the how the KSG and the TSZ signals look like from ACT, and you compared it with Illustrious.
Yeah.
Okay.
Do you mind repeating it for the people online?
Okay. Well, the setup to the question was comparing to Illustrious and other hydrosims. I think is it this plot?
So this is
this is the future. This is the current. So here's the KSZ and here's the thermal S.
right. I guess it's a combination of both these plots. I mean, my question was can you already constrain the different baryonic scenarios using this data?
Yes, so we were surprised and sorry, the question was, can you constrain the baryonic effects using these measurements? And we were surprised and interested to see that the data points don't agree perfectly already with Illustrious. So I think that theory work is ongoing. At this point, we just drew the Illustrious curve through here, and rather than look at the hydrodynamics of what's going on in these objects, we just showed the tension for now. Yeah, so already we're seeing some tension between the data and then what's in this Illustrious simulation. Is that helpful?
Yeah.
Okay. Oh, sorry. Yeah.
What is the physical motivation of stacking thermal SZ effects? In the sense that gravity does not have scale, so you can understand NFW, everything scales with whatever is supporting it, so you can stack it. But baryon physics has lots of scales. So why would the clusters be stackable?
So the reason for stacking is just the signal to noise.
Oh, I understand, but is there underlying theoretical, like, did you expect them to be self-similar or stackable, or?
Oh, so this is the CMAS, it doesn't say it. This is the CMAS sample, which stands for constant mass. So these galaxies are chosen to have a very limited range of halo masses. Is that where you're going with this?
Yeah.
Yeah, so it's not just stacking on every single object you can find, because what do you learn from that? No, it's really just taking this sample of objects that have very similar masses. And then there is an assumption that if they have similar halo masses, dark matter distributions, that they hopefully have very similar thermal SZ distributions. But that's a good question. Is there a big dispersion within the sample? We don't quite have the signal to noise to really investigate that very much. Like if you were to split the data into two halves and blow up the error bar of each half by √2, all of a sudden you can't measure too much anymore, because we're just kind of on the borderline of measuring these things right now.
On the using symbilancing to constrain baryon feedback. So how is the uncertainties of the baryon constraints compared to TSZ residues in measurement?
Yeah, we haven't really been thinking about the lensing to constrain the baryonic physics. Our approach, let me come back to that figure. Our approach here is just, is it important enough to lead to a bias on the fundamental physics, like the neutrino mass that we want to measure? I think that the kinetic SZ and to a lesser extent thermal SZ will be really good for constraining the baryonic physics. But with the lensing, the problem is you're only looking at all the matter with lensing, not just the baryons. So the baryons are a subdominant part of the total matter. And on top of that, you'd have the same problem of trying to distinguish between the baryonic changes and the fundamental physics changes, like neutrino mass or even dark energy. So yeah, no. So Simon actually had a paper on just what you're talking about, using the weak lensing shear to constrain the baryonic physics. But that was for not for CMB lensing, but rather for cosmic shear, lower redshift. I'm sure there's been other papers about that too.
One question from the audience, which is the tension in CMB related to high L multiple versus low L using Plake versus Commander?
Okay, so so the question was, about a tension between high L and low L in the primary CMB.
Well, is the tension that you refer to related to the high L versus low L?
Oh, in passing, I said there are some tensions in the primary
Yes.
CMB. And that is one of the tensions that people talk about. And then people also talk about, of course, comparing the Hubble constant from high redshift versus low redshift. And then another one that doesn't get talked about as much is okay, no, that's it for the primary versus low redshift that I know of. I don't know if anyone else knows any of this. But yeah, these splitting up the CMB into different multipole ranges and looking at the different cosmologies and also different likelihoods. There's been quite a few as well.
I have one question. If you go to the last slide, I think it was last but one slide. This is, you've shown these mitigation strategies and the removal of biases, right?
Yeah.
So there's, do the error bars blow up if you use any of these strategies? What's the difference in terms of, the trade space between error bars increasing versus bias removing?
So the question was, you can't mitigate for free. Any strategy that you do to try to mitigate these biases will necessarily inflate the error bars. It turns out that the error bar inflation is very small. It's in this plot. These error bars with the mitigation are actually larger than above, but these effects are not too degenerate, and so the error bars don't actually inflate as much as you might naively think. In particular, that using the LSST as a baryon proxy doesn't really inflate the error bar very much for a CMB-S4. Same thing with marginalizing over the baryonic effects. And I think the reason for that, if what you care about is neutrino mass, is that this black curve really does have a different shape than all these colored ones, right? So they're not that degenerate with each other. You just have to make sure that you're a little careful. Is that helpful?
Yeah.
Of course, if you had a fundamental physics parameter that did do something like this to the spectrum, like for instance, axion dark matter can suppress the power spectrum at small scales and keep the large scales unimpeded, then the error bars would totally blow up if you do this mitigation methods.
Any other questions? All right, then let's thank Alex again.
Thank you.